In this video, we'll look at some examples of damped harmonic motion. So first, we'll just talk through damped harmonic motion again. We'll do an example of finding an equation of damped harmonic motion for a specific physical situation. And we'll do an example on finding a damping constant. So recall that damped harmonic motion is if the equation describing the displacement y of an object in time t is y equals k e to the minus ct sine omega t, or y equals k e to the minus ct cosine omega t. For c greater than 0, then the object is in damped harmonic motion, and c is the damping constant, k is the initial amplitude, and 2 pi over omega is the period. So remember that we need c to be greater than 0 because if c was less than 0, we would have a positive in the exponent of e, which would mean that we would have exponential growth. So we need to specify that c is greater than 0. C is also typically given to us, or we can find it given the right information. K is the initial amplitude, so think of that as kind of the amplitude from our original simple harmonic motion equations. And 2 pi over omega is, as per usual, the period. So here's our first example. A string on a guitar is pulled a distance of 0.5 centimeters above its rest position, then released and allowed to vibrate. It is determined that the damping constant for the string is 1.4. Suppose that the note produced is a pure G with frequency 200 Hz. Find an equation that describes the motion of the point at which the string is plucked. So to begin, we try to get all of the information out of this passage. So since it says that the string on the guitar is pulled a distance of 0.5 centimeters above its rest position and then released, that should tell us that we're starting at a maximum. So we'll use k e to the negative ct cosine omega t, since cosine starts at its maximum when time equals 0. We also see that we have a distance of 0.5 centimeters above its rest position, so k would equal 0.5. We also read that the damping constant is 1.4, so c equals 1.4, and it produces a pure G with frequency 200 Hz. So after this, we have no more information to get out of the passage. So we've got K and we've got C. The frequency we need to convert into omega. So remember first that frequency is 1 over the period, and the period is 2 pi over omega. So we can plug this into the f equals 1 over p equation, so f equals 1 over p, which would give us omega over 2 pi. And if this equals 200, this should imply that omega equals 400 pi. And now we just pull all this information together, so we have y equals 0.5 e to the negative 1.4 t cosine 400 pi t. And that's how you find the equation, damped harmonic motion equation, given a specific set of parameters. Let's do another example. A stone is dropped in a lake, creating ripples on the surface. The up and down motion of a point on the surface of the water can be modeled by damped harmonic motion. At some time, the amplitude of the ripple is measured, and 20 seconds later, it is found that the amplitude has dropped to 1/10 of the measured value. Find the damping constant C. So in this situation, we're only really talking about amplitude, and we've conceived of damped harmonic motion as simple harmonic motion with variable amplitude. So since we're talking about just the amplitude, we only need to work with the amplitude part of the equation. So if, suppose we had an equation like this, we only need the first bit, the ke to the negative ct. So I can just cross this out just to make it clear that we're not working with that. So if we measure at some time t, and 20 seconds later we have a tenth of that first measurement, then we have the equation 1/10 of ke to the negative ct equals ke to the negative c times t plus 20. Alright, so this is a good place to start. We can just cancel some stuff now. So the k's will go away, and then we can break up our e to the negative c t plus 20 and multiply it through by 10. So we k's cancel, so we have 1 over 10 e to the negative ct, and then I'm going to go ahead and break this up, so we have e to the negative ct and e to the negative 20c, because we have to distribute the negative c through. So then we can cancel out these e to the negative ct's, and we're left with 1 over 10 equals e to the negative 20c. So then, since negative exponents flip down, we can do a little bit of cross multiplying. So we have e to the 20c equals 10. Now we just use our logarithms to solve for c. So we have the natural log of e to the 20c equals the natural log of 10, and 20c equals the natural log of 10, so c equals the natural log of 10 over 20, which you could then approximate. It turns out to be about 0.12. So damping constants are unitless, in case you're wondering why we don't have a unit in this case.